Hello everyone, welcome to our discussion of section 2.8 where we will be talking about three main concepts. As you can see on the screen, these are linearization, which is actually a way to use a straight line to approximate the behavior of a curve at a certain point. So it's then the second one is differentials. And because linearization is an approximation, then inherently it contains some error in it. For the measure of that error, to measure how much that error is in linearization, we have the differentials to help us with that. And then thirdly, the concept of a relative error. Now, a relative error is a ratio of the maximum error in the function value due to linearization. What is the maximum of that error? Take the ratio of that with respect to the size, the maximum size of the function itself. Okay, so let's begin with linearization, which is a linear approximation method. So basically speaking, or generally speaking, this is a geometric method or approach. So let's write it down to be concise. So this is a geometric that uses a straight line, hence the name linear approximation, right? Because it uses a straight line to do the approximation, to a straight line to model the behavior of a curve at a certain point. A curve is really a function of some form, right? So what we're really saying is that we're using a straight line to model the behavior of a function at a certain point. Again, because this is approximation, it naturally has some error in it. So let's just be a little bit more specific about this. So this straight line that we were talking about is actually a tangent line. So let's write that down. A tangent line at point A on a curve and the tangent line has this form. As you can imagine, it would be a linear form, right? So f of x would be equal to the function value, the function at that point that we're approximating the function value. So the function value at that point plus the derivative of that function at that point, which we learned that the derivative of a function at a certain point, it represents remember what it represents? It represents the slope of the tangent line at that point, times, of course, x minus a. So this is one form of that tangent line. Or also we can write it in this form. Instead of, since it's a line, instead of a function, we can call it with capital L, or line as a function of x equals to the same thing. So either that or this. Or that. So I know you remember this, but just for the sake of your note, let's just remind ourselves that f prime of a is the slope of the tangent line. Okay. So let's do an example to see how this is done. Suppose we want to find the linearization Lx of the following function, or some function, at A. Here's our function, f of x equals, let's take an easy function like sine of x, and of course A is given as pi over 6, or 30 degrees, right? So we just introduced the formula for linearization. So let's begin with that. We know that linearization has this formula is equal to the function at the value of the function at the point where we're linearizing or making a linear approximation, plus the derivative of the function at that value times x minus a. Okay. All right. So to do that in this case, we will need the function value at pi over 6. That's that piece. We will need to calculate the derivative of this function at this value and multiply it by x minus a. And whatever we find is the tangent line that will approximate the behavior of the curve at that point A, at no other point at that point A. Okay, so that line, once again, once we find it, it's going to approximate the behavior of this function at that point. Okay, so let's do that. First of all, the f prime of x, or the derivative of that function, is simply equal to cosine of x, right? Now we want to find the value of that f prime a, the derivative at that value a, which is pi over 6. So f prime at pi over 6 would be cosine of pi over 6. Cosine of 30 degrees is square root of 3 over 2. We know that from trigonometry, right? That. We also need the value of the function itself at a, right? This one. So let's calculate this piece. So f at pi over 6 is equal to, move this up a little bit, would be equal to sine of pi over 6, which is 1/2. Okay, so now let's plug in these values into this linearization format. So we have Lx, it would be equal to the function value at pi over 6, which we just found it's 1/2, plus the derivative, the value of the derivative at a, which we just found it's square root of 3 over 2, times x minus a, and a is pi over 6, like that. Okay, so let's simplify this a little bit. So we have 1 over 2. Let's distribute this, right? Square root of 3 over 2 times x minus, we have square root of 3, so pi minus pi square root of 3 over 12, like that. Okay, let's take the common denominator between this term and this term. And that would be our intercept. So we have the square root of 3 over 2x, that, and taking the common denominator there, it would be 6 minus pi over 3, 6 minus, so plus 6 minus pi times square root of 3 over 12. Okay, so let me see if I can show on a piece of scratch paper what I just did. Well, let's see. This is a piece of paper that I don't need in a short while. So what we did, we took the denominator between those two, so 1/2 minus pi times square root of 3 over 12. So clearly the common denominator is 12, and this one is already 12, so we don't have to worry about with this fraction, but this one will multiply the 2 by 6. 6 times 2 is 12, but we also have to multiply the numerator by 6, right? So then now we have the common denominator, 6 times 1 is 6, minus, this stays as it was because the common denominator was already there, minus pi times square root of 3. So this 6 minus pi times square root of 3 over 12 is what I have here. And this is the line that can approximate the behavior of this function at point pi over 6. Okay. So that's basically the linearization concept. Now note that, of course, this is because it's an approximation. It's an approximation, right? That's what linearization is. It's an approximation of how at a certain point, then it naturally contains errors. errors. So the second concept that we mentioned, which is the concept of the differentials, these differentials help us measure that error in that linearization process. So now differentials help us measure these errors. In the process of linearization. So all these three things connected, all these three things are connected, and that's how they're connected so far. And we'll get to relative error as well. So let's talk about differentials. And this was item number 2 on the list. So we already know that if we have a function that is given as such, if we have f of x equals y, let's say, right? Then f prime of x, so we already know that if we have that, then we have f prime of x is equal to dy over dx. Okay, dy dx. Now, the differential is defined as the following. Let's call it, so let's give it a symbol. The differential dy, that's the differential, is defined as following. Dy equals f prime of x times dx. So we basically, if you multiply both sides by dx, on this side the dx cancel out, you end up with the differential dy equals f prime of x times dx. Like that. Okay, so that's the differential. Like that. Okay. So let's just explain this. Even though I said it, I want to write it down here, that dy so this is the amount that the tangent line rises or falls. So i.e. the change in linearization. And of course, f prime of x we know is the slope of the tangent line. So dx is the slope of the tangent line. And dx, I meant f prime of x. Sorry, let me correct this. So this is not, I meant to say that. So it's f prime of x, which is the slope of the tangent line. Let me correct that. F prime of x is the slope of the tangent line. And then dx is the change in the value of x. And I'll draw a graph for this too, so it all makes sense. So then dx is the change in the value of x from x to x plus delta x. So in other words, it would be delta dx is equal to delta x, but you go from x to x plus delta x, the change in x is delta x. Delta is that small triangle that you see is the Greek symbol we use to represent change of value in mathematics. So let's draw a picture for this. And I want to draw an xy axis. I'm off the screen, I know, but I'll move the page up so you can see what I'm doing as I draw this line. So let me move this up like that. And then also a vertical axis here. Like that. Okay, that's better. So we have x, and then we have y. And let's suppose that we have some curve that goes like this, like that. And then we can pick any point. Let's say this point here. Let's pick 2 points, one here. And let's pick another one that is here. Let's say here. And if we draw a tangent line to the curve at this point, at let's say this point, let's draw a tangent line to the curve at that point. So I'll try to make it as clean as possible. Like that. So let's call this point P. So we'll call this point P, and let's call this point Q here. And so the coordinates of that point, let's just say that they are, for the x value, we have x, right, like that. And for the, and by the way, this curve represents the function y equals f of x. And for the y value of this point, we have f of x, right? So, like that. So this p is, this p has coordinates x comma f of x, right? The y value and the x value of that point. Then we have this q. So let's call the q, the coordinates of that. Of course, I have to label the x-axis first. So let me drop a dashed line here. And we're going to call, if this is x, this would be x plus delta x. And delta x is this distance. Okay, from here to here. From the x-coordinate of point P to the x-coordinate of point Q. And let me write here that x would be x plus, this is the x-coordinate of point Q, x plus delta x, times the function value at that x plus delta x, like that. Okay, and let me just say that this distance here is dx or delta x, either way. Okay, different notations for the same thing, basically. Okay, so then dy would be the change. So this is the change in the x value from point P to point Q. How about the change in the y value? Because these are the variables that would define, right? Dy, dx, and all of that. So let's identify them on this graph. We've already identified dx. So dy would be, if I continued this dashed line from here to here, so this would be from here to here, it would be dy. From here to here. So this would be dy. Let's see. Dy. Okay. I think so that would be that, like that. Okay. So I think that completes that figure. So we defined these variables, and then we showed them as much as possible on this graph with the f of x and dy and dx. Okay, so like that. And of course, delta y, we don't have delta y, but delta y would be the difference from here to here. Okay, so that's just dy. So this is just the geometric definition of these variables, right? So these are just changing value of x and all of that, slope of the tangent line. These are geometrical definitions of these variables. But with respect to the function, they also have a description or meaning. So let's also mention that as well. I might as well try to, let's see, I might as well try to fit it right underneath this graph. I think that's better. So here is another definition of those same variables. So we have dy. So also dy would be the maximum error in the value of the function due to approximation. Right, so the maximum error, because the line obviously is not tangent to the curve at that point. So this point would be represented by this point on the tangent line. We might as well extend this curve and call it that. Well, let's call it R. Okay, and then dx would be the maximum error in the value of the independent variable. That would be x. And then let's see, so then we'd have that, and then we have f prime of x, of course. F prime x is the derivative of the function. Okay, so let me add something here. This is dy, and this would be from here to here would be delta y. Okay, so that's the projection of the y value on the curve on the line, which is approximating the behavior of this curve. Using this tangent line, we're approximating how this curve is behaving. So there's an error associated with that, also with this delta y. That point is represented or projected on the line at that point. So there is an error associated with that. Okay, so then thirdly, we have to talk about the relative error, which has a small formula also. So this is simply as the relative error equals dy divided by y or so that we either with this notation or equals f prime of x divided by f of x. like that. Okay. So let's do one, maybe two examples in applying these formulas that we just learned about. So in this example, we want to find the differential of the function of the following function. Which is y equals 1 minus v squared divided by 1 plus v squared. Okay, so let's do that. So the differential, let me bring back that page. What we would need, the dy is the differential. And so that is equal to the derivative of the function we are given times the change in the dx, basically. Okay, let's find that. In this case, we don't have x, so we will have dv, basically. So let's find y prime first. And we know how to do that. Y prime, this is a quotient rule, right? Take the derivative of the numerator, multiply it by the denominator, subtract the derivative of the denominator multiplied by the numerator, divided by the denominator squared. So derivative of the numerator is minus 2v, right, times all of that, 1 plus v squared, minus the derivative of this, which is 2v, times all of that in the numerator, 1 minus v squared. Of course, all of this divided by the numerator squared. Okay, so let's simplify this. Move this up a little bit. We have minus 2v times 1 is minus 2v. Minus 2v times v squared, we have minus 2v cubed. Minus 2v times 1 is minus 2v. Minus 2v times minus v squared is positive 2v cubed. All of that divided by 1 plus v squared squared. Okay, so now we can simplify this a little more. We have 2v cubed and minus 2v cubed add up to 0. So we have y prime minus 2v, that's minus 4v divided by all of this, 1 plus v squared squared. Okay. Now, we took the derivative of course, y with respect to v, right? That's what we just did. So instead of y prime, let's substitute for y prime with its equivalent notation. So we know that y prime, in this case, is equal to dy dv, right? So let's substitute for y prime for that. So we have dy over dv equals minus 4v divided by 1 plus v squared squared. Okay, so let's multiply both sides by dv. What happens? Then on the left, dv cancels out. On the right, we have all of this dv, right? So multiplying by dv, we have the differential, which is dy equals minus 4v divided by 1 plus v squared squared dv. Okay, so this is our result. That's the differential, okay, which measures the error in the linearization process for that function. Okay, so that's 4, that's page 4, and this is, so let's do another example. This is a little more applied than the other one, which was purely mathematical. So suppose here we know that the radius of a circular disk is given as 24 centimeters. With a maximum error in measurement of, let's say, 0.2 centimeter. Okay, given that, we want to know, or we want to use differentials to estimate the maximum error in the calculated area of the disk. Okay. All right, so what do we know in this case? We know that the radius, let's take it as r, is equal to 24 centimeters. That's for the entire disk. We know that from elementary geometry, we know that the area of a disk is pi r squared. And so what would be the differential of this? If you take the differential, this is the function, right? And we want to use differentials. So if the area of a disk is that, from elementary geometry, what's the differential of this? The differential is dA, right? Let me bring back that slide. So the differential of any function, f of x equals y, it's dy dx. In other words, the derivative of y with respect to x. Here, we don't have y and x. Instead, what do we have? We have area and radius. Obviously, area is a function of the radius. So our differential would be dA equals the derivative of area with respect to the radius, right? So take the derivative of this. What do we have? We have 2 pi r, right? And then dr, right? The derivative of r, dr. That's the slight change of in r, or delta x, or dx. Instead of dx, we have dr. See, instead of dy, we have dA. Instead of dx, we have dr, and that's the differential. And the derivative which we took times dx, but in this case, the derivative times dr. So this is the differential given this area. given this function for the area, this is the differential. Okay. Oops. Somehow, when I was not noticing, the screen went out of focus. Sorry about that. Let me try to focus the screen. Okay, that's better. So that being the differential, now we can plug in for the values that we know. We have dA, which is what we're calculating, 2 pi, r, in this case, we were told it's 24 centimeters. dr is that 0.2, with a maximum error in measurement of 0.2. So times 0.2. So this would be equal to 9.6 pi centimeters squared, right? Because the units of this is centimeters, the units of this is centimeters, centimeters times centimeters, we have centimeters squared. So this we can assume to be the maximum error in the calculation of area. So this would be the maximum possible error. Maximum error in the calculation of the area. So for part B, which is the differential, right? That's the meaning of the differential in this case. For part B, they want us to calculate the relative error. So what is the relative error? And they also ask what is the percentage error, which is once we know we calculate the relative error, then we convert it to percentage. That's all. What is the percentage error? So the formula for the relative error, let's bring that back. It was dy over y. So in our case, instead of y, what do we have? We have dA. So instead of dy, we have dA. Instead of y, we have a. So it would be dA over area. So it would be dA over a. And of course, these are, a is a function of the radius, right? We know that. So dA, we just calculate the differential, right? It's equal to 9.6 pi. And the area we already know, it is equal to that, pi r squared. Right? So pi r squared, and in this case, the radius was given to us as, so let me write it first down, and then this r was 24 centimeters, right, for the entire disk. So 9.6 pi divided by pi times 24 centimeters squared. So of course pi and pi cancel each other out, and so we have 9.6 divided by 24 squared would be 576. So the relative error is equal to this divided by that, 0.0167. That's what I got. But we also have to calculate this as a percentage error, or percentage error would be this times 100, so 1.67%. Okay, so that's just the application of linearization formulas and the differential and relative error formulas. I hope this helped you to better understand these three concepts that were discussed in this section. So with this section 2.8, we have wrapped up our discussion of chapter 2. Next will be coming up, the next few videos will start in chapter 3. Thank you for watching this video until the end. For now, have a nice day, and I'll see you again next time.